So in this example, we got a kid that throws a ball that is 20 meters away. She throws the ball with an initial velocity of 15 meters per second at a 40 degree angle. And we want to know how high up will the ball hit. So basically we have a situation here where we've got a wall and we've got a kid just throwing a ball up at an angle. And we have this initial starting velocity v naught, and the ball goes a certain distance in the x direction, and it goes a certain distance in the y direction. We just want to know how high up it gets. So basically what we do is we take that initial velocity vector, and I kind of drew it pretty steeply. I'm going to draw it a little less steeply here just to kind of help us visualize this. And this is going to be our v naught. What we had to do here, just like usual, is break it up into, we had to resolve it into its x and y components. So we could call this one Vx naught, the initial or starting velocity in the x direction. We have our Vy naught, our starting y velocity. And if we look close, we can see, well, hey, we've got a triangle here, and we know we've got this angle here, where that is going to be our 40 degrees. This would be our hypotenuse, this would be our opposite side, and this would be our adjacent side. So we can treat these just like a regular triangle. We also know that V naught, just because we mentioned it here, V naught, that hypotenuse, is going to be 15 meters per second. So now that we have our kind of our visualization here, what I want to do is list our variables. And like usual with these types of two-dimensional motion problems, I want to make sure that we keep our x's separate from our y's. And what we know is that the distance that the ball travels is 20 meters. We also know that the initial velocity in the x direction is going to be the adjacent side to this triangle. And because of so ka toa, that would be ka, which is, we go back to our equation from before, the hypotenuse times the cosine of theta is going to be equal to our opposite side, which is our Vx. So what we do then is we can just solve this right now. We can put our 15 meters per second, which is our hypotenuse, times the cosine of theta, which is 40 degrees. And when we solve for that in our calculator, we get 11.49 and some change meters per second. So that's how fast the ball is traveling in the x direction. For the y direction, well, first of all, you might be wondering, well, where's the acceleration? There is no acceleration because this is a situation where it's the horizontal velocity. There's nothing speeding up and slowing it down. We are assuming that there's no air resistance, and so we're not even going to bother with acceleration. So that's going to come into play because our v naught in the x direction, our initial velocity is going to also be our ending velocity, our final velocity. It's going to be the same velocity throughout. Not so in the y direction though. So I'm going to say, well, our change in direction, or I'm sorry, change in position in the y direction is what we're trying to find here. How high up did it go? So we're trying to find that. And our velocity, our starting velocity in the y direction is, well, that is going to be the opposite side of this triangle. And so ka toa, this is so, which is sine. So we're going to take the hypotenuse times the sine of theta, and that will be just like before. Oops, that's a 15, we'll squeeze that in there. 15 meters per second. That's our hypotenuse of the triangle up here, times the, I almost did it. Let's just undo that. That will be the sine of the angle 40 degrees. And when we put that into our handy dandy calculator, we get 9.64 meters per second. So that is the initial velocity in the y direction. And because it's going upward, we're just going to leave that as positive. It's heading up, and up is positive. We always refer to up as positive. That's just arbitrary, but that's just how we do it. And that's important because there is an acceleration in the y direction, and that is downward, a negative 9.8 meters per second squared. So we have an initial upward velocity, and we have an initial downward acceleration. So the next thing we want to do here is we're going to try to find how long was this thing in the air before it hit. And we do that because we know exactly how far it went, and we know its speed, and so therefore we can figure out how far it went. And in order to do that, we're going to use the kinematics equation that goes like this. So the change in x, the change in position, is going to be equal to the initial velocity in the x direction times time plus 1/2 a in the x direction t squared. And you might be saying, hey, wait a minute, Mr. Jern, you said there is no acceleration in the x direction. And that is correct. And because of that, we get to do something fancy here. We get to say, well, this is going to be 0, and anything times 0 is going to be 0. So all this is just going to be canceled out to 0. So it's going to be Vx naught times time plus nothing. So let's figure this out. Actually, we don't want to know. We want to know time. So let's divide both sides by v naught. And so time will be the change in position in the x direction divided by v naught. And when you do that, you basically, if we look up here, how far did it go in the x direction? Well, it went 20. I didn't write that down originally. It went 20. Oh, I did write it up here. So I should be doing this in the blue to match, but it's too late now. Meters, and our initial velocity, so we're looking blue, is going to be 11.49 meters per second. And so the time is going to be, when we divide that out, 1.74 seconds. So that is important. In fact, I'm not going to put a box around it because it's not our final answer or anything, but it's important that we know that time, because since we know the time it was in the air, we can figure out how high up it's going to get in that amount of time. And so that's exactly what we're going to do. How high up in that amount of time? That's what we're going to find out. So we look at our kinematics equations once again, and in keeping with the theme of alternating colors here, I'm going to go to blue to show how to do that. And there's one equation that will work here. And now, if you have the list here, this is all going to be x's. I am changing those for y's because we're talking vertical now. So delta y is equal to the initial velocity in the y direction times time plus 1/2 a acceleration in the y direction times time squared. And you might be like, hey, wait a minute, that looks very familiar. That's because it's the same equation that we used where? Down here. So it's the same, literally the same equation. It's just that down here, we were talking about the x's, and so everything was x. So change in x, the initial x velocity, and the x acceleration. So that helped us to find the time, but now we are talking about the y's. And one of the main rules we follow here is never ever mix x's and y's. X's and y's are independent of each other. And so you don't put any x's in with your y's in these equations, and you never put any y's in with your x's in these equations. All right, the only thing that goes back and forth is time, because it is a scalar. It does not involve any direction whatsoever. So to figure out how high this thing went, we're almost there. We are going to start substituting in. And so our initial velocity in the y direction, as we came from, over there, it's in green because I messed up the colors, 0.6 meters per second, times the time, which we got down here, 1.74 seconds, plus 1/2, 0.5, times the acceleration. And acceleration of gravity is down here again in blue, or in green, negative 9.8 meters per second squared. Multiply that by time squared, and so we just take 1.74 seconds and square all that. So what's going to happen here is we're going to get some things canceling out. The seconds here will cancel out with the seconds here, leaving us with meters, which is a good sign because we're trying to find the distance it traveled upward. These seconds squared, well, this seconds over here is going to get squared, so that is going to cancel out with both of these seconds and leave us with just meters once again, which is a very good sign because our units should always work out. So when we plug this into our calculator, we're going to get this positive number, and we're going to get this negative number over here, because when you multiply these numbers, you're going to get a negative number. So when we plug these numbers in, just be very careful in your calculator. I'm not going to work all this out for you. You could do the math, and what you should get is a positive 1.7, we'll just say 7 meters up. And that, ladies and gentlemen, is our final answer. So when the kid throws the ball, she's going to hit the wall 1.77 meters high.